Actually, maybe the remote can you hear me, by the way? You cannot hear me. Can anyone say if you can hear me? Yes, so you can hear. You cannot switch on your camera, or can any of you switch on your camera? Okay, because I wanted to ask a question to all of you, actually, to both the real and the remote people. It's more a question to the remote people, but my question is actually if there are some people in this whole class that would not be able to come to the real event, right? In particular, from those that are remote, maybe there are still some people that are in other countries that don't get a visa or something. That would be a strong reason to keep this. But otherwise, we could also just switch to only real, which would make my life a bit easier, let's say. So in particular, those that are now remote, can you really comment on that? Is that something that would inhibit you from really coming severely? I mean, like you are not in the country during the whole semester. So maybe you could type that into the chat if you have some reasons against it, and otherwise I would think carefully about maybe switching this off at some point. Okay, for those that are here, is there a strong opinion on either? I mean, obviously it's also an option for you to sometimes stay at home, like Florian also mentioned that if people are sick, then maybe some people are sick and come because they have to come and so on, right? I don't want to create wrong incentives, but on the other hand, it's just a flipped classroom lecture. So I think if you skip one of these question and answer sessions, you can still watch the videos, read the manuscript, do your exercise. I mean, you can do everything without coming. So I would actually maybe in any case say to each of you, whenever you feel sick, stay at home, right? That's a general rule for anything, right? And having said this, I think we should be free on deciding what the group wants. Okay. Can you really hear me all the time? Can you also say something? Yes. Okay, so Moritz Graf is not able to come. Send me an email. Okay, so I think you should be able to hear me now. Can you say something so that we can hear you?
Hello, hello.
But don't you have microphones? Yes, we can hear you. Can you say something, someone? Hello, hello.
Hello.
Yes, wonderful. Okay, great. So next time maybe just answer briefly, because I want to hear both sounds, right? That you can hear me, but I also want to hear you. Okay, but now let's just focus on what we do anyway. Solution. It's about question and answers. We are now at example 4.2, I think. That means somewhere in the manuscript, in chapter 4 already, the dual of an LP, I think, was where we stopped. That's right? You can correct me because you have read it and you have. I think this is like lecture 4 ended, and we should have watched lecture 1 to 4 now. So we are on page 32. And so we talked about basically an overview of fundamental concepts, right? That's the first chapter. Then we had the second on types of optimization problems, so different topics. And then the third chapter was on context optimization, definitions and a bit of theory. And then in chapter 4, we are now already talking about the Lagrangian function and relativity. So we did already pretty much, if you think of it, since I'm meeting the last time. So you are going to ask lots of questions today. So as usual, I would like that everyone tries to prepare one question, at least, so that you would have a question in case no one else asks your question, you would ask it. And maybe I should also ask a question myself before you raise your hands. Did anyone read exactly until, let's say, page 32 or even more? So arrive at page 32 by reading. 2, 3, 4, 5, 6, more or less. Very good. And who already finished at least reading chapter 1? The first one. I mean, the same people should raise their hand again. But who finished at least chapter 1, like basically started reading. Okay, that's very good. And I would really welcome everyone to try to be in sync so that you have read exactly what we should have read at the first group. Please try to get into the rhythm. Okay. Okay. Yeah, maybe for you this is new, so I should explain a bit how we usually structure it. I will collect questions now. I will not directly answer them. I will just write them down, and then afterwards I try to optimize my path through these questions in order to answer them as understandable as possible in the best order. Okay, so I would just collect a few questions, and you could also say, hey, please repeat this part, or explain a bit more on that, or whatever. So this is how it should go. You have a joystick, so to say, and you control me, right? That's the idea. Yeah? Give me input, and I will do what you ask me to do.
I didn't quite understand the proof for the left side of complexity for continuous functions.
Just say it's a page, maybe.
21.
21. Okay. For C2 or for C1? Theorem 3.1, right? What should I say proof again? Namely that, which means if something holds, if you have this inequality, then it's a convex function. Okay. Okay, good. Something about convex. Questions that you like me to discuss today? You know what I like about this lecture hall? It's sunny. That's probably why it's, I mean, it's particularly sunny at this time. It's, yeah.
So right at the beginning, you have one, there's this word compact.
Yeah.
What is compact?
That's a very quick answer. Compact is means bounded and closed.
Okay, so what is bounded and closed? Maybe that's the best question.
Bounded means you can find a big circle which covers it, right? And closed means that every convergence sequence converges to a point in that set. But basically, think of any set that is, so to say, this is bounded, right? It wouldn't be bounded if it would be somewhere infinity. And it contains its boundary. That's closed. Closed means it contains its boundary. So basically, a set that contains its own boundary. Okay, I could also add one. This would still be a compact set together. They would be still compact. So it's just if you think of, for example, x, so that x is bigger than 0, this is not closed. Actually, it's also not bounded because you can get too big infinity, right? But for example, this one, x so that 0 smaller than x smaller than 1, right? Also not closed, that's not a good set, but it's bounded, right? It's an interval. It's the interval, but it doesn't contain the boundary point. And if I make this, for example, this set, this is closed and bounded. And that means compact. Okay. So your background is not in mathematics, I guess.
That is correct.
Yeah, well, yeah. So it's yeah. Just accept close and bounded and read these concepts if you like. Okay.
Section 3.5 standard for convex and
3.5 page 24.
So boxes. Applying inequalities
Standard, sorry, it's 24 and 25. So it's a theorem or which one? What is the question about?
the question is why G the linear inequalities must be applied.
Ah, you mean example 3.5 or section 3.5?
Section 3.5. Yeah, section 3.5. Then I mentioned in the lecture that G always has to be applied. Or equation 3.5b, there equality
Yes, 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 yes. Okay, 3, 5, b. That's actually 3, 5, b. This equation actually is better. X equals b. Why?
is always applied.
Why not nonlinear, right? Yep. Okay. Yeah. I think I will explain that later. Yes.
It's not linear or it's convex. The equality is what can we do that in practice?
So if we have a non-convex, that's already non-linear, but convex equality. Yes. It's a very good question. So, sorry, convex, non-linear convex equalities, right? That's the question if that exists. Right? Okay, that's a long question. Okay, other things? Questions, maybe also from the chat? Yes, there is a chat question from the chat. Chapter 1, you talk of theorem for the existence for unconstrained coercive function. What do you mean by coercive? Okay, that's actually something beyond because I think it's not even in the script, right? Or, okay. Other questions to be collected? Yeah.
Example 4.2.
Which one?
4.2.
Yes. The last one. Yeah. The dual of the other. To do this again, or is that a question?
Why the increment is minus.
Sorry?
Increment of n function, why it is minus infinity.
Ah, yes. Okay. Somehow, if there's something related to these, I would welcome this question still, and otherwise, we'll just start to answer some questions. Have another round of questions. I would like to ask you, I would want to make a break, and I think around 3, maybe even a bit earlier than 3, if you can remind me that I wanted to make a break. I would be grateful. And then we do a 10-minute break. Hopefully it's still sunny outside or something. A bit of fresh air. And it's liquid, so there'll be a bit more space. So I think we have answered that. In the order where they have been asked, that's probably okay. Okay, so this question is now we find one. And what we want to prove is that, I mean, we have a function that is differentiable, and then we also know that this function satisfies all x which are in the domain. We just have the right language. X in the same domain. X and y as in the domain of the function, and that maybe I draw the picture. Y and x, right? X is here. Find y, and we want that the function is above its Taylor series. That's basically what it says. That means that f of y is above or equal f of x as another f of x transpose y max. Okay, so that is what we know. And this holds that we want to show that for all x and y in omega and for all t in 0 and 1, right? Holds that, and now we have this other thing. Maybe I call this, no, I call it differently, x bar and y bar, right? Just to make them different from the other thing. So here I have x bar, y bar, and I want that the line is above the graph, right? It's a different statement, so I want that actually the function at the linear interpolation, which is actually f of x bar plus t times, I mean, here this function value, and then the linear interpolation is this f of y bar minus f of x bar times t. When I'm at this point, and that should be bigger, right, than the function f at x plus t times y bar minus x bar. Right? That's what I want to prove. And there are probably many ways to prove it, but actually one way would be that you take these 2 points. I mean, for any of these givens, I need to construct basically something that has to do with the derivative. Here is no derivative, but there is a derivative, right? So that's a big difference. And what I will do is I will actually choose the point where I am as the linearization point. Yeah? I think that will, I hope this will do the trick. So what was the question? Right, so you can come out, or maybe anyone can interrupt me if necessary. Okay, so basically I choose this as, let's say, the x in that theory, right? So I choose actually this thing will be x. right? I define that sheet. And then I plug it into the other theorem, and then I will use, and that theorem then tells me that this point and this point will be above, right? So I know that now from, so the proof is this given x bar y bar t, define, yeah, we need to find, yeah, I mean, we want to prove this, right? Prove 1 is 1. Okay, and so now I'm going to say x this line in the middle, so it's x bar plus t times y bar minus x bar. And now at this point, I will use this and I will plug in for the y once the x bar and once the y bar, and it should hold for both, right? So I will just say f of x bar is bigger than f of x plus another f of x transpose, and then here I have x bar minus x, right? That's the first application, and then the second is f of y bar is now bigger than x plus another f also at this x, and y. So this is now two things I have. And what I want to show is actually that this value f of x is smaller, that's this one, right? Than what I have here. So let's see if we can get that. So I isolate this value. That's already the answer. Maybe I multiply these two inequalities with t. Minus t. Yes, sorry, one with t and the other with t minus 1 minus t, right? So this should be 1 minus. So this is the t. So I multiply these two things and add them up, right? So that maybe that should maybe do the trick. So then I get the left side is this, right? And the right side would be this, and then the question is what happens with these things, yeah? Okay. So I need to add these two things up. But I can probably show that these terms cancel, but let's do it. You see what I mean, right? So I have here now 1 minus t of x bar plus t y bar. That's bigger than f of x, which is already the right thing, right? And then I have here something which is like 5 transpose, and now and here I have actually this thing is t times y bar minus x bar, right? That's what this is. And this one is actually, what is it? It's actually it's 1 minus t. Let me think of it. And it's y bar minus x. So it's the remainder exactly. It's 1 minus t of y bar minus x bar. Can we see it immediately? Maybe I have to, it's still to be correct. Y bar minus x bar minus t, y bar minus x bar is equal to 1 minus t, y bar. And it's fine. Good. Okay. So it's indeed that's all it is, and then if we multiply with t and with 1 minus t, then I get something must be wrong. It's x bar minus. Here's a minus, right? And so that must be with a minus, right? Is that? So subtract the x. So better than to let me try. So I take this is the definition, right? I'd like that into this one, and then make it slow. So it's And then you see, okay, you get these, and then you just remain. Okay, and then I get here 1 minus t times minus t from this, and then at the very end I have y power minus xy. I still have this term that is t, and then 1 minus t, and then these two will be multiplied with that. And that's a vector, and it's multiplied here. But now the fact is that this is the same as this negative, so this whole thing is equal to 0, and it is what we wanted to go. Satisfied? Okay. So the trick is actually to have this point itself as a point where you take the linearization. Thanks for the good question. Okay. So now the question is about section 3.5. So what is, if you have an equality, sort of convex, non-linear inequalities, right? Equalities. And so maybe to just think of it, so the first thing is if you have a convex function, we call it HI, right? I mean, in this lecture, I think we have done all of this. Okay, let's better call it Fi, right? Fi being smaller than 0, that would be the right thing. If I have an equality where I say g of x is equal to 0, then I could also equivalently express it. Let's say this is a scalar thing just for the starting point. If it's more than one component, I can always stack them together. But let me just say this, I can just replace by this being smaller than 0, right? And minus g of x is smaller than 0. I mean, that's trivial, right? So you just basically press it. I could also say, another way to express the same thing in one line is actually this, right? So the upper bound and the lower bound are 0. So just formally we have proven that if you have a convex function, then the sublevel set of the convex function is a convex set. So right. So in that sense, if f is convex, then you know this is convex, right? Now if G is convex, then this part will describe a convex set. And this minus g of x is a concave function. So its sublevel set is not necessarily convex, right? So it's actually one of the two sides which creates the difficulties. So if you have a convex function that should be equal to 0, then actually the convex function being smaller than 0 is not the problem, but the convex function being bigger than 0. That is the problem. So one can very easily show examples, right, where you would have, for example, a convex function. Let's say you have square plus y square, right? That's a convex function. I subtract 1 to make it nicer. And I say this function is now phi of x and y. That should be equal to 0, right? And that's actually a circle, right? So this x and y. So this would be a circle. And so if you would replace that by two inequalities, then the good one, this one, this would correspond to the inner part of the circle, right? So it's forbidden to be outside. This one would correspond to the outer part. Right? So the inner part is forbidden. That's the non-convex part, right? So in some sense, and then plugging this into that one, then only the middle will survive, only the boundary will survive, right? So you see very pictorially in this example what is going on here. So the problem is, let's say, this non-convexity. And so in that sense, you you can, I mean, it's impossible to prove that for a general convex function, if you make it equal, that the level set would be convex because, sorry, the zero level set, which is this one, right, is convex. That's because it's just not the case. So we cannot prove it. I don't know if that was already more or less your question, but so what I concluded from this is that the only equality constraints that I can actually prove that they will be leading to convex sets are linear inequality constraints, because only linear functions have the property that both the g and the minus g is convex. You see what I mean? So that's the reason, because I mean, there's no other functions where both their negation and themselves are convex, and that these are the affine functions. So that's the reason why we restrict ourselves to affine functions. And there was a related question. So are there some nonlinear convex inequalities were asked it? Yep. Maybe I should say that, of course, you can always make from a linear inequality something nonlinear, if you like, right? So let me just give you an example. So I have 18 x plus the number I call theta equals 0, right? So that's a vector, just a scalar constraint. So something that says that it means to think of x in multi-dimension 1, 2, right? It's something like this. And only this is allowed. Now, of course, you can change this in many nonlinear ways, if you like. Yeah, I could, for example, put this into a tangent. It would be a bit stupid to do, but I could, right? The tangent is through 0, and I think it's something like that, right? So it's making it a bit nasty. It's nonlinear, it gets to infinity and so on, but it has still the same zero level set, namely those times versus 0. Yeah? So it's a nonlinear transformation, which makes from a nice set something not so nice anymore, right? So you can have special cases, right, where even a nonlinear function leads to affine sets. I mean, this is called an affine set, right? Basically, plane or hyperplane. So in that sense, there is no, it doesn't, I mean, the reason I write ax plus b equals 0 for only affine is because only for these cases I can guarantee it will always be convex. Doesn't mean that there might not be some special case, even the feasible set is convex, though the function is really non-linear. And then maybe I should also say that there is some very interesting cases. For example, this lunch I was even discussing about one of these. So sometimes you have equalities which are like this, and you still think that somehow, but this, I don't think it's non-convex. And it turns out that some problems you can prove that the multiplier associated to some of these constraints, if you can prove that the multiplier has a certain sign, always in any solution. So you could say, whenever I have a solution, the multiplier of this b must be positive, for example, right? That means that this multiplier has the right sign and this one has the wrong sign, so to say. That means that this is binding and this wouldn't be binding. No? Of course, formally, these two constraints, I mean, violate LICQ because they are linearly dependent, and also, so they would be both active all the time, right? Because the upper and the lower bound are pressing against each other. But practically speaking, you could omit the one that's not binding, which has the 0 multiplier. So if, for example, if I have an optimization problem, let's just make a very simple example. I want to minimize y. And I have x and y, both in R, right? And subject to my function x squared plus y squared minus 1 equals 0. So now I could look at this, and I don't know if we would be able to prove something about the multiplier constraint. Probably we can't. But at least I don't, right? But if someone would tell you, this multiplier is always positive, let's say you could replace it with this and with this. But you know that this other constraint, this one, the bad constraint, the one that is not convex, right? This constraint will never be binding, so its multiplier will never be zero. I mean, if you can prove that, then you can show that it's enough. Right? And your solution is here at the bottom, right? That's the minimizing of y. It's actually, it turns out that it satisfies, this constraint is active in the solution. So if it's active, that means it's residual zero, so the equality is also satisfied, right? So basically, if you can show that the good side of your constraint is always active, as a positive multiplier, then you could replace your problem with that. And even if you can't prove it, you could always just formulate, let's say, this problem without that. You omit this part. So you could formalize it, solve that, and then you get at least something, that you know is a lower bound, because it can only be better because you omitted a constraint. So actually it made the feasible set too big, right? So it allowed all these points in the middle, while in reality they are all excluded. So you allow all the bigger search, so you have a relaxation. And if this relaxation turns out to be a feasible solution to the, if this constraint is active, then you have a solution. Then you have a global solution, and you are, so to say, so in that sense, it's not completely useless to know that an equality is convex, but formally it's not convex, and there are, easily constructible cases where this inequality is also binding. For example, if my objective would be to minimize the distance to this point, one half, for example, I think I could easily show in this case that the minimizer is here. It's a non-convex minimizer, and I could not, I wouldn't get that for the, you see it already from this picture. The relaxed solution, if you, let's say, that's, I have now y minus 1/2 squared plus x minus 1/2 squared, and if I have the same problem, apart from this is replaced by that, right? Sorry, it's the other way like this. That's the objective, right? Like this now. And you see that the relaxed solution will be actually the point here, that's 0, and that the optimal solution is here. So, and it's not here. This is also a stationary point, but it's, this is the optimal one. And so it doesn't really help you to look at the relaxed one, because it's not satisfying the equality. This is partially answering your question, or fully answering?
Yeah, but we could just consider the equality x squared plus y squared equals to 1.
Yeah.
And then it is a circle, and every 2 points can be connected through the line, and the line again lies inside the circle. Then that is a convex. So why do we consider it as intersection of two inequalities, whereas we could just consider it as one equality?
Wait a minute, so I think I don't understand. So if I have the circle, right? So let's say here, this is the circle, right? The inner part is excluded, the outer part is excluded. The disk is with everything, the circle is only the boundary, right? So if I take this point and I connect, and it's not in the set. I'm not sure if maybe we discuss it later. Okay, it's clear. Okay. That's not a convex set. Okay, does it answer all the questions around quantities? Okay, then the question, what is the coercive function, unconstrained coercive function? And I think I'm not sure exactly absolutely the right function, right? But actually, it says that if you go, I mean, there's a function f, it goes from Rn to R, and I think f is coercive. Now I'm a bit wobbly, right? But the meaning is roughly that from if x goes to infinity, that implies that f of x goes to infinity. Right? So in some other words, if you think of it, you could also say the minimum. I think this would be a nicer way to say it. F of x, where x is bigger than R, right? So these are all the points which are out of this circle, right? And I call this phi of R. So I expect that this minimum will become bigger and bigger because I make these circles bigger and bigger. So I have less freedom. So this phi of R is for sure is monotonously increasing, right? By definition. And so I have my circles and I make them grow, and I look for the minimum point that's out of these circles. So this minimum will be somewhere, but it will actually be only getting bigger when I increase my circles, which are forbidden, right? So this monotonic is monotonically increasing, and I think it's coercive means just that phi of R converges to. Okay? So it just means that your function is going to infinity when you're going out. Which in particular implies that your level sets, your sub-level sets will be bounded. That's the beauty of it, right? So when you have such a coercive function, you fix a level set, some finite number can be big, arbitrarily big, but for the set of f x smaller than some number big M, this x, this set is all I think this would be another equivalent statement. So basically, coercive functions are things that go to infinity when you go away from the from zero, so to say. Okay. So we touched infinity now. So to continue with infinity, there's the next question. Was also about infinity. So we have in example 4.2, we did something, or I just somehow magically said that something must be minus infinity, right? And I say, oh, something is minus infinity. So I ask the first question. So I define a set, right? Let's say I have a set of all x, so that x is smaller than 0, right? Just a set, maybe smaller or equal to 0, right? That's actually, if you think of the set of x's, it's containing 0 and then all the points. So it's this point, all these points, right? So the maximum value, right? So what is the supremum of s? 0, right? But what is the infimum of the set? That is minus infinity, right? Because it's the smallest value that is contained in the set. And so now here in this example, we have a slightly more complicated expression. We have some vector. Let's say we want to look at the set of all the infimum of the set of yeah, so here we have a vector, I call it maybe V, and so x and x is in R. And so maybe I should this is a bit, this is already like optimization like language. So this is like a set and this is like the values. If I translate it to this language, I would say S is now the set of V transpose X, where X is element inside and right. So it's the image of this, of the whole of Rn under this linear map V transpose X. You could also say it's a collection of all numbers alpha, so that they exist in X in Rn, so that alpha equals V transpose. Another way to frame this. It's a bit funny, right? But you could also say this. Yeah? So it's this collection of these values alpha. And now if this vector is not zero, right? If the V here is not zero, then for any alpha, I can find an X which satisfies this, right? So basically, this set is equal to R if V is not equal to 0. And if V is 0, if V is the vector of all zeros, I mean, if this is the vector full of zeros, then the only thing is, and the set is equal to 0. Right? So that's basically the two cases that can happen for this set here. Do you agree? When either the V vector is 0 and then the only possible point is 0, and otherwise it's the whole of R. So, so basically this is the informal of R is equal to, what is the informal of the whole set R? Minus infinity. Yeah. And the informal of the set 0 is just 0. And so that's how this came. Because the vector V, of course, is C minus A transpose. And then C transpose. That's, and then you get it. Okay. Yeah. Perfect. Yeah. Bit late. But I think we should do our break now, and afterwards we collect new questions and we do another round. Yeah. I suggest we really do a 10-minute break, so we meet back at 15 and 20, and I will 15:20, and I will aim at ending at 15:50. Okay, that will be my end time. Promise. Okay, so can you help me? Let's open the windows and we just go outside. Any of the lights will go outside.
In der Vorlesung extra Zeit haben.
Ja.
Bekommen wir das Skript.
Bei mir beziehungsweise bei
Nicht Informatik.
Erdgeschoss 1, 2.
Dann komme ich am Montag.
Super, schön. Ja, haben Sie jetzt erst angefangen mit dem Studium? Oder?
Nee, ich bin eigentlich weiter, wenn ich nur ein CCS habe, was anschließt, und der Vorlesung ist ausgefallen, jetzt wegen 6 zu viel, aber das war das nächste, was ja.
Soll ich
Ja.
1 und 2 Come sta?
Super, Dankeschön. Bis dann.
Remember me?
So where do you have now?
I started my PhD.
Sorry, you
I started my PhD.
decided that
Started.
Yes, perfect.
Yes.
Should be right.
With any certificate and what?
Yes, okay, the industrial one, right? Yeah, very good, yeah.
Yeah, I started last month. And
And so you're supposed to get Bosch or?
also a university, like twice or once a week, like at least once,
Yeah.
sometimes twice,
Yeah.
with the chair of scientific computing.
Ah, okay.
Finished it good?
What's the professor?
Yes, yoga.
Sorry?
Yeah, yoga.
Okay, great. So scientific computing. In Bosch, what is the unit there? Is it like Renning or somewhere?
It's fine. It's actually it's in the department belongs to Upstart, but like the project site is in finance. So it's really close to me.
Yes, Bosch.
Like they have their own research for like testing on driving, so they have the testing lab in finance. And yeah.
What's the title of the PhD?
Like, I don't know a specific title, just it's about optimization. Based optimization. Like scenario based optimization. So my first task was optimization. Yeah, so I was having Bayesian optimization. And then with the university, like there's something called Sparse Grid. Yeah, mostly black box optimization. So his main method is Sparse Grid, and he wants to like to see that, like try to make it the best performing on the card. So
That's not the question of what optimization problems you must have, right?
I went up to Leonardo and Leningen because we also like the PhD base at Leningen, so I also have to see it. And I'm so jealous of him that you actually support him. Thank you.
Okay. So, yeah, we could close the windows. Maybe we should close the windows. Think about the next step.
Then they always say approximately P equal to P transpose and P by something. But this the
So the question is about positive semi-definite matrices, right?
system my every matrix or just for symmetry. Of course, that's
Yes. Yeah.
Because in the Slater,
Later.
it,
Later.
you give an example that was not in the script.
Can you write it down or something?
Yes, I think so.
Yeah. Later condition counter example, right? So when we do this, we will have to write down the counter example. To which page?
I think it's 31, definition 4.5.
Yeah. Mm-hmm.
why the virus class, if you still move from one, why when it's like non-empty contract, there will be a rule behind.
Or sorry, non-empty in contact, right?
Yeah, non-empty contract, there will be a global minimizer. Yeah, that's the definition. But I don't understand there, because if it's like a plane, then it's, everything is the same. Not that doesn't mean that we have one minimizer, right?
Yes, actually, we refer to this situation, right?
Yeah, exactly.
Yeah, the interesting thing is, I can directly answer, right? A minimizer, all these points are minimizers. All minimizers doesn't need to be unique. Right? I mean, you can be that's a bit different. I mean, you can be the best student in an exam, right? And another person can also be the best student in the same exam if you both got the same number of points, right? So in that sense, the language of a minimizer does not need to be unique, otherwise it's a unique minimizer. That's a special thing. Okay. Maybe I directly answer this positive. This is actually indeed only for symmetric matrices. You only look at symmetric matrices. Yeah, so it's the downside of the symmetric matrices.
Yeah, but for square matrix, then we also say something more.
I mean, we can try. So you want to just say, I mean, what is, I mean, the set of, I call it Sn, right? It's the set of all matrices A and R and cross N, so that A is equal to A transpose, right? So that's A. That's called, maybe that's not the right abbreviation. Sometimes people call it Sn. Let's just call it Sn, right? So this would be the set of symmetric matrices, and then typically one notes by S this. So it's actually all A in Sn, right? So that A is rooted definite, which is also the same as being A in Sn, right? So that for all Z transpose A, Z is bigger than 0, right? That would be a very simple way to define it. Right? That would be another state. Couldn't we define? So the question, could we define like what's your name? The first letter of the name? Sorry? M. So we define M, N plus, right? And that would be the set of all matrices in Rn cross N. So that for all Z, Z transpose A, Z is equal to bigger than 0. We could define that set, right? All bigger. We don't care about symmetry or not. And now I think we can probably characterize that set directly, and that's interesting. I think this, any matrix, right? For any A, you can write like A bar plus A tilde, right? Where A bar is elements in Sn. So, yeah. And A tilde is, I mean, that means basically A bar is equal to A bar transpose, right? And A tilde is equal to minus A tilde transpose. That's a standard decomposition, right? So you can see specific, yes. And I think we can do that, and then we can define, I mean, A bar is actually A plus A transpose divided by 2, and A tilde is A minus A transpose divided by 2. I think this is the way to decompose it, right? And so now there's one interesting thing, because positive definiteness and what you do with these matrices is, I mean, the eigenvalue criterion, which would be equivalent for symmetric matrices, is a bit difficult here because these matrices might have non-real eigenvalues, right? Okay, but so eigenvalues I don't touch, but if I use this definition, and I think that might be possible to use, it would actually mean, and now the interesting thing is, Z transpose A times Z. Think of this, Z transpose A times Z is equal to the sum Ij, right? Of Z I, A I, J, Z, J. And interestingly, this is symmetric in I and J or Z, right? So you also write actually like a trace. That would be one way to go. Of Z transpose times A. Another very funny way to write this. Maybe this doesn't help me actually. I think I will not brainstorm. I don't know if it's useful for anything what we do, but I tried to do it. So what I because this is that I mean, let's do it this way. I continue this way, so I said I, and here now I put A child plus A tilde I A, I claim that this is actually equal to Z equals A bar. So I think that only the symmetric parts are right, because the I and the J here are actually symmetric. So I could easily transpose this, right? But then I get the negative, and if I transpose this, I get the same. I think the easiest way to see it is it's just, I mean, it's linear and it's this decomposition. So I can have this sum and I can have this sum. And for this sum, I see I can do this product, right? So what is A? What I wanted to show is actually A tilde Z transpose equals to 0. That's what I want to show. And that is easy to see, right? Because that is equal to Z transpose A Z minus Z transpose A transpose Z by 2, and this is the same, right? Because because it's the transit. I mean, that's a transpose of each other, and that's just a number of 0. So in that sense, so the interesting thing is that the set is actually, if you think of it, it's the set of positive definite symmetric matrices plus the skew symmetric matrices. Right, so you can add any skew symmetric matrix and we will change this equality. Maybe the set could be interesting for someone, but usually, I mean, this set doesn't have even a name or something. So it's always restricted to symmetric matrices.
Can I have 2 more questions to the list?
Yes.
So I have one question on one word that you used here, like so you used global optimizer. Is that the same as the global minimizer function and so on? Like,
yes.
Okay.
The optimizer could be all minimum.
Okay.
And I mean, my language is, I mean, an optimizer can be max or min, but usually in this lecture it's min, right? Yeah. And I use minimizer for the point that achieves the minimum value, right?
Okay.
This is sometimes not, I mean, I'm probably sometimes sloppily say this is a global minimum and I mean the point, right? But I should say it's a global minimizer, the point, right? I mean, if you are the best student in the class, you got 60 out of 60 points, right? Then I would still say you are, yeah, I don't know, that you're maximizing, you're maximizing the points, right?
I get it. That's supposed to be like a minimize or maximize it as an okay. And the next question was in the first order optimality condition.
Yeah.
There's a definition there. If the point if x is like, let's say the nabla, like the Taylor series.
Yeah.
The point is bigger or equal to 0. So and then now page 26, the point
26. Yes, an optimality condition for convex problems. Yes.
Yeah, so that saying that the x star would be the global optimizer if it's like bigger or equal to 0. So one thing I mean later on you put in the next page, like whenever it's
we prove something there, right?
That it's equal to 0 then the other side. But I didn't get why it has to be bigger, because if my function is going down, I have a negative slope of my tangent, and then why would not that be considered a global optimizer? Then if I'm going down and like there's some constraint, and the lowest point is on the right corner.
Yeah, yeah. So let's just look at your. So what's your example? So you want to have function that has like an, I mean, in one dimension, x, right? And the function is going a bit down here, and here's a down, right? Yeah. This is forbidden, let's say, and that's a function of x. Yeah. And so you say, what do you say? That's a global optimizer, yeah, exactly. Yeah.
And then, but that slope would be negative, right? Because my number x star will be negative.
And it's one low, this is will be a star. Now the interesting thing is that you know, I mean the gradient, right? In this case would be a negative number, right?
Yes.
And that's just scalar, so I can just write it's a negative number, right? Because it's a one-dimensional example. But this convexity condition, what does it say? It says that the star transpose and y minus x star should be positive, right? For all y in the feasible set.
Yeah.
And now the feasible set is this set. Right? So this could be a y, for example. Y minus x is it's negative, no? It's negative times negative, and that is positive.
But my y wouldn't be the one with the x star, like that y in the moment x star, or that's
for all y in omega, right? So you can also choose x star, but then this is anyway 0, and that's also 0.
I get it now.
Or you can try this one and this one, any of these points, they're always equal. So you don't have a counterexample. Okay, great. I think we had nearly all from the center thing. So maybe before we collect more questions, I would invite you to write down this later question. Right? I mean, we are on page 31, and I give you the chalk if you like. If you like that. Maybe it's, is it fast?
Yes.
Okay, so maybe first, let's say what's the definition? It's definition 4.5 later, right? Maybe before we give you the example, I want to read it loud and then we can all recall. So the Slater condition is satisfied for convex optimization problems. It's only restricted to that. If there exists at least one feasible point such that all nonlinear inequalities are strictly satisfied. Yeah, so that, More explicitly, for a convex form, we must have affine equality constraints, and the inequality constraints functions can be either affine or concave functions. Thus, we can, without loss of generality, assume that the first Q1 inequalities are affine and the remaining ones concave. Then the Slater condition holds if and only if there exists an X bar such that, and then we say, and now that I should write it down, right? What is it in X bar? X bar Slater, so to say. Point Slater pointer, yeah? If and only if X be equal to 0 and feasible point, of course, and also convex. The affine inequalities are bigger than 0, the affine ones, and others must be strictly non-linear convex or concave. So that's what it says. So if you think of an example, I mean, that's on the equalities that make everything just difficult to visualize. But if we have a lot of linear inequalities and then also one non-linear one, right? Then the question is, okay, it's a condition, right? So it's sorry, it's not even sorry, this is right. The MRP satisfies the Slater condition if there exists an R. So it's not even LICQ is something that refers to a point, right?
This is one singular.
So here it just says there must exist some point. That's it. That's it, right? So there must exist some point, and let me just check which point would satisfy this set of equality. This point would satisfy it, right? This point also satisfies it. This point would satisfy it. This point would not satisfy that condition. So that X bar shouldn't be this point. Yeah? Because that's a curved inequality here. These are the affine ones, and that's the curve. But I mean, the point is that at the moment that none of these points exist, it's already satisfied, right? So this problem is also a feasible point, but it would not be relevant for the Slater condition.
But in our example, we had
Okay.
2 lines.
So circles
Yes.
and 2 lines.
Yes, on each
Side here.
No, closer lines to the circle.
In the middle, or where?
H2 equals x1 and H2 equals minus x1. In the middle, yes.
That's an exercise.
No, it leaves this right.
Just give me the number. So what is the constraints? So one is actually a convex one, like x squared plus y squared minus 1 smaller than 0, right? Probably the circle.
I think yes.
Yeah, okay, so I will come in the circle. Okay. What was the other constraint?
It's qualities and H2 equals x1, H2 equals minus x1.
Yes.
So there are 2 lines closer to the center. And the physical is everything in the center of. You understand?
Okay, so I have this.
Yes.
They're arbitrarily close to each other. So and this side is forbidden. And this side is forbidden. Right?
Yes. And then we have one more curve.
One more curve.
Yes, one more curve. And there's only one point that satisfies
Okay.
at the top.
Yes.
That does not satisfy the subject.
Yes, exactly. That's a good one. So when you know I had another circle that is like this one, right? Okay, yeah. And so, okay, so should we quantify it, let's say? So this other circle is probably something which is centered around, I mean, this x and this y, right? So it's centered around 2. It's probably like plus y minus 2. Yeah, minus 1 smaller than 0. That would be the other inequality, I guess, right? And I mean, the situation is already okay, right? Because I mean, even these 2 points, this is sorry, this would satisfy us later, right? But at the moment that these two circles are having only one point remaining, then the Slater condition would be violated actually.
There's only one point.
I mean, this has only one feasible point, and I think it's actually x equals 0 and y equals 1, right? And then this is satisfied and y equals 1. Also, this is satisfied, so this is exactly this point here, right? And there's no other feasible point because the circles are so far from each other. So if you have these two constraints, you have a convex optimization problem. They are both convex constraints. And your feasible set is non-empty, it's one point. Your feasible set is even convex, right? Because it should be convex anyway, because it's convex constraint. But it doesn't satisfy the Slater condition. Because there is no single point where you can make these two inequalities strictly active. Yeah? Actually, yeah. By the way, it would already hold if I had this circle, I want to do circle and then I have like one in the linear constraint. If I push that above, so that there's only this one point missing, it's also violating Slater. So at the moment that I make my feasible set too small, so to say, I think that's doesn't satisfy the Slater. I forgot actually why did we use this Slater condition is something that is people need to prove strong duality. That's why it's interesting. But we didn't do it in this lecture. I just want you to know about it, let's say. And maybe I should say that linear programs have only linear inequalities, right? So by definition, they satisfy Slater's condition all the time, right? Because they have only these two and these don't exist. So in that sense, quadratic programs and linear programs, they always satisfy Slater's condition by definition. They cannot be different. And so they always have a strong duality.
And like reason behind why it can also not be equal to 0 when it's non-linear.
I mean, I'm at the moment not exactly sure what was the problem where the proofs break down. So I cannot exactly say what is. But maybe I could. Yeah, maybe I think I can already give you a bit of indication because it's also really. I mean, in a sense, if you have such a situation like one feasible point only, right? You, for sure, at this point, LICQ is also violated. I don't know if that helps you. No, we don't have LICQ yet, but it comes later, I think. But if you think of, I mean, you can usually expand functions by the first order Taylor series, and you get a pretty clear picture of the feasible set. So if I'm, let's say, having a suggestion like this, and I'm at this point, I could linearize my two functions, and that will actually make a linear approximation of my feasible set. And that is then a polyhedron. So, and that's something that is very much related to the theory because it's the tangent cone. And so the tangent cone is, you can get it from the linearization. And if you had two affine inequalities like this that press against each other, they are already linear, and so you will get this whole set, right? But now you add a little bit of curvature to one of them, and at that moment you get, instead of the whole set, you get only one point. Even if this curvature is infinitesimally small, right? So very little curvature will already make it. And so your linearization of that current function will still be flat, and so the linearization will not tell you anything about the feasible set, so the neighborhood of the tangent. So roughly speaking, the Slater condition will ensure that your linearizations of the functions can generate the tangent cone. But this is too far. Let's talk about it later. Remind me of that question if you like later. Yes.
Can you explain that segment cone theory?
Yeah.
It's same as linear programming, just with the linear.
Okay, so the question is linear, can we say that a semi-definite program is the same as linear program, but just with a linear matrix inequality? Yes, I mean, it's not the same. It's like a generalization. Yeah, because this linear matrix inequality is a much more powerful object, let's say more complicated and more powerful. Maybe one interesting question is every LP also an SDP? And the answer is indeed yes. SDPs can be easily used to model also LPs. And the trick to do that is actually, you would say, an SDP, right, means that you have some matrix function we call the G of X, and that should be positive. I mean, that's what it is, right? And how operates on the distribution is the FR. There would be one particular choice of this, which could be that you have a matrix G of X, but it's constructed so that it's an A1 transpose X plus beta 1. This entry, that's actually one number just, here 0, here 0. Right? Here I could put into this element an A2 transpose X plus beta 2. So I basically fill all the diagonal elements only. And then I created a huge matrix, which I finally depends on X, right? That's qualitative. And if I impose this to the positive definite, then this is the same, because positive definite means all eigenvalues will be positive. It's a diagonal matrix, so it has the eigenvalues visible here. So it's the same as saying that A1 controls X plus beta 1, A1, M transpose X plus beta M, big N, whatever. Is positive. Right? And that is a linear. These are linear. You can actually indeed make it, but of course it's much more powerful when you have these plots in the really matrices. And then the cone of semi-definite matrices is a very interesting object. It's a really, yeah. I sometimes say it's the queen of convex programming, right? Semi-definite programming is like the most, like a chess. It's like powerful class of solvable convex optimization problems. I mean, for which you can find solvers. So whatever, I mean, any QP, any LP, everything I can formulate as an SDP, but I can formulate some other things with SDPs which I could not formulate. For example, finding this smallest eigenvalue of a symmetric matrix or such things, minimizing the. Sorry, yeah.
How we can formulate the QCQP as the SDP is not.
Okay, so you are really testing me.
This is like
SDP. So that's something that perhaps I will actually switch on the light, I think. Okay, so let's try it. I'm not so sure that I will manage that. So QCQP as an SDP. I can directly.
I studied it just for examples.
I'm not so sure actually. But I know that we can formulate a QCQP as a second order cone program. So usually I would actually do it like second order cone program, and then this one you can formulate as an SDP. That would be one way, and I think that would be the standard way that you could see if we can get it directly. Let's just start. We have one inequality, right? How do we call it here in the manuscript? Do we have it somewhere, like a QCQP?
Okay, example 3.6.
Sorry?
Example 3.6. Page 25.
Yes, QCQP. So we have one, let me just take D transpose X plus 1/2 X transpose B X. That should be smaller than here. So that's what we want. Now we want to sort of say, formulate that in terms of, I mean, the feasible set that is described by this set, we want to express as something with arbitrary. I don't exactly know how to do that. I mean, this is obviously not affine, right? It's quadratic. That's also what makes it interesting. So I'm not exactly sure, but let me try to go this way. This is probably the way people. That way is, I mean, basically, maybe I should say what this. First define probably the square root of the matrix B, which is the symmetric square root of B. Yes. So for the B1/2 B and also B1/2 B1/2. That's something that you can always define for a symmetric or semi-definite matrix, right? So B. Semi-definite, that means there exists such a B1/2. So now I can, this is B1/2, which is just a change of this matrix. I can just write this whole thing B1/2, transpose B1/2, X in X transpose, right? So I could now write this whole thing as C plus C transpose X plus 1/2, and then I have the true norm of B1/2 X, the true norm squared. That's another way to write this whole thing, and I now change this a little bit, and I just say maybe not. I should say that I don't solve spontaneously. I think I try a bit and then I give up, and maybe. So let me just define this as being there, so that should be okay. Actually, I know that this is positive, right? So then this must also be positive. So I will just have now X equals Z, so that's 9 that way, right? And now I have 1/2 Z. Yeah, it should be smaller than minus C transpose X, right? This is actually bigger than 0 by definition, right? So I also know that this must be bigger than 0. And I think somehow this now yeah, I'm a bit unsure about. I somehow want to make this equal to T squared. Or is T squared, which is a bit dangerous, right? But I think this is what I want to do. So let me try to do this. Like I want to half. And this is of course the equality I will keep on from now. So this is smaller than T squared. And T squared is equal to minus P minus C transpose X. So now I didn't change anything apart from doing some stupid nonlinear constraints, and I try to think what I now. Okay. So now I have something which is again quadratically explained problem. I didn't gain anything from this. No, so I think I give up. No. Okay. Yeah. What I wanted maybe to just tell you, I wanted to carry it from here. Second order cone program form, but I think I don't deal with this one. So I think I look it up. Yeah, so I will think about that question and answer it hopefully next time. If you find out an answer, you can also write me. Yeah.
At least you need this there. These emails there, whatever.
Yeah, so scalar would be a bit easier. Yeah, so maybe we should just try x squared smaller than 1 or something. Yeah, but of course, if you have a scalar also, then the set is so true. It's just so I think, okay, but anyway, our time budget is over. I think I keep this as an exercise for myself, right? And I just want to say that there are beautiful books on progress optimization. I think this one you would maybe easier find in it's called Modern Progress Optimization. In Tal and Nemirovsky, and that's a beautiful book as well. Okay, good. I will look it up myself. But thank you for this very good question and all your questions. Thanks you. And have a nice weekend. Thank you a lot. Bye.